How's it going?
It's going well.
Good.
It was a really interesting presentation you guys gave.
Thanks. Thanks.
Yeah, it sounds like you guys did a lot over the summer.
Yeah, it's a lot of time. A lot of overnight.
So are you all mostly grad students or can undergrads join as well?
Yeah, we're welcome both undergrad and grad students.
Okay, great. Yeah, I'm an incoming first year, but I'm pretty interested in joining the team. I filled out the application form, and
I
it's
guess
really exciting work.
we will go over all the application very soon, and maybe actually after this showcase.
Yeah, that's I don't know if there's going to be more joining for perception. I thought the entire group was going to come in here. There were so many questions from perception, but I will moderate this panel, and we'll do maybe even we could do some quick introductions so you know who's who. But I'm going to just message the main room and see if we should get started or not. We'll see if we're going to get any more people. But is it Renaud?
Ronak, yeah.
Ronak, yeah. There's a really great opportunity, I think, to get some younger people, especially first years, onto the team. When you say first year, do you mean like incoming to MIT?
Yeah,
You just started.
I'm incoming first year, but I have done like a lot of research in autonomous driving. So
don't worry about it. We'll get all that out in the details of the application. But we want younger people to keep the tradition going. Like, you know, you got to learn at some point, and it can happen earlier on or later. It's fine.
For sure.
More the enthusiasm we're looking for. So good to see you here.
So Sophie, I was really interested in the work that you mentioned where you were kind of speeding up LiDAR by inferring the point cloud. So I was just wanting to understand what the output space of the model was, because you kind of discussed that there was 2D LiDAR and the 3D LiDAR that you were projecting the 3D LiDAR onto a 2D space, right? So are you predicting in that 2D space or are you predicting in the 3D space?
I'm predicting the 3D space. I actually projected the point cloud onto the RGB image rather than not just projected that onto the 2D point cloud. Yeah.
Got it.
Yeah.
So just to, go on. Just to add to Ron's question, so just so I understand properly, you're basically taking the depths from the 3D point cloud, projecting them onto the 2D image, and then taking in the images at each sort of, at each interval, and then trying to predict the depth from that.
Our input is RGB image and the 3D point cloud. And what we are doing is project the 3D point cloud color onto the RGB, project the 3D XYZ coordinate, because that's in 3D space, and we project that onto the RGB image to extract the RGB color for our model. So our input is like XYZ coordinate from the point cloud data and RGB color from the camera image. That's the input of our model, and our output is the 3D point cloud.
So you keep the RGB information, is that right? So you just add extra channels for the depth information.
We didn't use any depth information because we are using the coordinate of the point cloud, like XYZ.
Okay, got it.
We don't use depth information. Yeah. And
so what information are you getting from the cameras? Because right now we
are using the RGB color we are using the RGB color from the camera.
So you're projecting that onto the 3D point cloud.
Yeah.
I see. Okay.
Yeah.
Yeah, go ahead.
Yeah, because this model we trained it on self-supervised method, and we actually have because we to like better pruning our model, we have trained our data on synthetic data set using the supervised method. So like for now, for the real world data, we are like use self-supervised method. So that's why we use the XYZ point cloud and the RGB color as our network input.
Are you using any of the sort of like calibrations between camera and LiDAR at all? It sounds like
Yeah,
it's a
yeah,
purely machine
that's what we
learning.
do. Yeah, the calibration between the camera and the light.
But it sounds like right now this is like very purely like machine learning approach. Is that correct?
We pre-process the camera and lidar data, and then put it into our network input.
And that calibration is provided from the car, or do you have to do any work?
Yeah, because our machine have those data for us to do the calibration, and after we pre-process it, we put it into our model.
That's nice.
Can you describe the self-supervised approach that you take when you're like adapting this to like real life, when you're not just doing like imitation on synthetic data?
The reason why we do self-supervised is because real world data, we actually don't have ground truth motion.
Yeah.
We only have ground truth lidar, but we don't have the motion. So that's why we are doing the self-supervised for the real world.
So my question was, can you describe the self-supervised learning method that you use?
Yeah, sure. We basically design a loss function for the self-supervised method. We have because the lidar point, they are like totally random, right? They don't have, they're not like camera image. They have a specific like sequence and RGB color. So we basically we use nearest neighbor to calculate the loss function between the two ground truth point, between the point cloud data, and then add another function, another loss function, like a cycle loss function. So in this case, like, yeah.
Right. For a nearest neighbor loss, it's basically like a transfer distance computed like between 2 point cloud. So basically, because when you have like a predicted point cloud and you have like a ground truth point cloud, they're just like two sets of points, and they do not have like a deterministic like order of the point. So if you want to compute some kind of distance, you probably need like some kind of like earth moving distance or like transfer distance to compute.
Got it.
Hey, let me jump in. We have a good couple of people who hopped in, which is great. For the conversation, if you guys, we're still a pretty small group, but if you guys want to raise hands in the participant window, that would be helpful. And we also have like quite a few questions we could go through from the general Q&A chat box. If anybody wants us to do that, we can. Claire, go ahead.
Yeah, I just had a question about the presentation from earlier. I remember you guys compared the difference for the mean squared error between like single input and double input, and I was just wondering what exactly did you mean by double input? Is it like the combining like the 2D map with the 3D point cloud?
So it's actually like two consecutive frames as input. So basically, like when you want to predict the future, you can like have like different like levels of information. For example, you can only use one previous frame to predict the future frame, but in that case, it's kind of like ambiguous. Then like to like kind of like reduce ambiguity, you can also like include more frames as the input so that like it can have a sense of, for example, the velocity of the car, so that the future is kind of more determined in this sense. So here, what we mean by like double input is basically like we have two frames as input.
Okay, got you. Thank you.
Sure.
Cool. Yeah, Ronak.
Yeah, so I was wondering, you mentioned that you take like two consecutive frames, and one thing that I was wondering is, have you considered trying stereo cameras? So have you like two cameras located in two different sides of the vehicle to get depth estimates?
Right, but actually because we have the LiDAR sensor, right? So in that case, you already like kind of have the depth estimation. Like it's kind of a pretty accurate like depth estimate. So
I was just thinking in terms of, because you mentioned that one of the problems with LiDAR is its speed. So a stereo camera is like much faster potentially for processing. So.
Right, exactly. It's actually like another approach of having like LiDAR. It's like called some research in the academia called pseudo LiDAR. So basically, you can like use the stereo images to synthesize the LiDAR point cloud, because you can actually compute the depths, and then you like basically render the depths into a 3D space, and you have the point cloud. One issue of that, like approach is actually the pseudo LiDAR has pretty like different distribution from the real LiDAR distribution. So if you want to have like a single unified 3D object detection model to process like both real LiDAR and the LiDAR like rasterized from the depths is kind of like non-trivial. So that's the reason why we actually want to like have the LiDAR predicted from the real LiDAR. So it's kind of like still in a similar distribution and can be like captured using like a single unified like detector model.
That makes sense. Thanks.
Sure.
Anybody else who has want to jump in? Shakar, yeah.
Yeah. So I had a question for Matt. I was curious about your strategy for perception, but it sounds like you're using two different networks to figure out depth or perception metrics. Can you go over what those two, like why you need the two different networks and what they specifically do? I kind of missed that.
Yes, absolutely. So, so there's really three steps to that replication and point painting. The first step was in inferring information from the camera so that you can use that to augment the point cloud, paint the point cloud. And the third step was then to use that painted point cloud to develop a better 3D object detection model. So if we look at step one, we need a model that can give us infer some information about the from the camera image. So specifically in the point painting research paper, they used a semantic segmentation network by the name of DeepLab v3 plus. And so what that class of architectures what that's all about is it taking an input image and then outputting an image where at each pixel, say pixel, X equals 30, Y equals 45, you have a score for what class of object that pixel belongs to. Okay, that pixel belongs to a human, that pixel belongs to the lamp post, that pixel belongs to the car. So that's one model. And then in the third step, we use a 3D object detection model, which maybe GGen wants to discuss a little bit further, that as input takes in a LiDAR point cloud and then has learned the parameters such that it outputs not only the class of the object in the 3D point cloud, but also where it is. So this is sort of like the two.
Wouldn't the camera image do that for you? Like when you pass in the camera images?
So this kind of goes into that's a good question. The camera image, so this kind of goes into the trade-off of camera images and LiDAR point cloud. With camera image, when you have a lot of texture, but it's in 2 dimensions. And it's not always easy to then determine the location of something from a 2D image in the 3D world. And it's so we use that information from the camera image to then augment the 3D because it's the 3D point cloud, because as research has shown, the results of 3D object detection, figuring out where objects are in the LiDAR point cloud, is far better in LiDAR methods. And that's actually what motivated this research paper was, the researchers found that how LiDAR methods were the best. They surpassed many other ways of doing 3D object detection, but now how can you fuse information from the camera to make that better? But trying to do the 3D object detection from the camera image is not,
that makes sense. And just to follow up, you talked about porting most of your software into C++ or like a faster framework. What exactly are your sort of strategies for that?
Is this question for me specifically?
Or does it, if it involves the rest of the team too? I mean, feel free.
Yeah.
I think overall, like So overall, like currently we're like all the pipeline is like kind of implemented in Python, right? So we're using PyTorch to have all the training, and currently the inference is also done in PyTorch.
Yeah.
kind of like a common practice if we like convert all the code to like C++, like for example using TensorRT, but it's actually non-trivial. Then like the
Is it
model.
because your networks are very like non-traditional?
Sorry.
Is it because your networks are quite non-traditional and it's not easy to convert?
The major reason is actually like for the 3D detection, like Matt mentioned. So actually, it's actually a lot of sparse convolution operation. For that one, it's actually not that well supported like in any like deep learning libraries like TensorFlow, like PyTorch. They do not have that kind of support. So for this, we actually have a specialized library implemented to support that. But because it's like a specialized library implemented by us, so we probably need to spend more efforts to like convert it to like, for example, TensorRT or something like that. So that's the main like difficulty we found.
For background context, Shikar is our last year perception lead, and he did a lot
Yeah,
of
so
TensorRT.
I did a lot of work with perception last year, but it was on a car which is running much slower. So I'm very aware of the pitfalls and the struggles that you guys probably have right now. But it sounds like you guys are doing a lot of cool work, so I applaud you guys for that.
We can get you back on the team there, Shikar.
Yeah, I'm trying to free up some time right now, but
Balance that workload.
Yeah.
Hey Ronak, keep it coming, man.
Okay. Sorry, if anyone else has any questions, feel free to.
Everyone feel free to raise your hands or throw a message in the chat if you want. Otherwise, we're gonna let Shikar and Ronak keep running the show.
So one question like that I kind of put in the chat was, you mentioned that you do simulation. So how do you handle the transition from simulation to real images? Like I've read in the literature that can cause a lot of problems with like perception.
I think we probably are going to use data collected from real world. Like, I think like that's definitely like something we can try like to use like something, for example, seem to real, but it's really like challenging. So currently like the data set we're using, for example, for the perception, we're mostly using like Newsync or Kitty data set. They're all like real world data sets. Okay. For this like, challenge, I think we will also like probably like have some data collected and annotated so that we have some data. And also like another thing why we want to do the self-supervised, like for the selfies part, is also because that we probably need to collect the data by ourselves, so and we don't want to like annotate that many data. So that's also one major reason why we probably want the self-supervised approach instead of like a pure supervised learning approach.
Got it. That makes sense.
We actually have look at a simulator like Color and find out like the LiDAR point distribution is so different from the real world. So like we don't want to bother tackle the sim to real challenge.
Like even in academia, there's definitely like some attempts in academia like trying to close that gap, like paper like LiDAR sim or something like that. I think for our case, we probably will just stick to like using real data if we can collect enough like data from the.
Actually, a quick question: Did you guys know? Were we supposed to drop back out to the main room?
Just click leave room and go back.
But did we have a time? I thought Crystal was going to pull us back.
I think she said, yeah, that was it. She said this is going to be the end after this is done.
Okay, got it. Yeah, so we have a couple more minutes. I actually had one quick question. I'll let you hop in. Claire, did you, I don't know if you mentioned it, did you say, were you an MIT student?
Yeah, I'm a student.
What year were you?
I'm a rising sophomore.
Oh, cool. That's awesome. Yeah, I wasn't sure. We don't have like everyone's buckets of where everyone's coming from. I don't know if anybody else is, anyone else is in here as a student or is coming from one of the outside organizations.
Yeah, I'm a student.
Yeah, you two are great. We have one from BJR2KJ. Let's let you ask your question. Does anybody want to answer that in the chat? We'll just talk a little bit about radar. which I know is
Yeah.
something that our team isn't. Oh, go ahead. Hey, ask the question. Hop in.
Yeah, just got myself off mute. My name's Jeff. Sorry for the cryptic handle there. Yeah, just I'm wondering, I saw that radar was mentioned. Just want to know what role that plays in the scenario, if at all.
Right.
Yeah.
Radar is kind of more noisy, so currently we haven't like explored that. But I think for the radar, like I think currently a common practice is just like convert it to something similar to LiDAR and having them concatenate together. So if we want to explore that, like probably it just like somehow merge that to the LiDAR input in the future, I think.
Another kind of sensor fusion, like LiDAR, radar.
Right. I think
But
later.
radar is on our side, just not yet.
Sorry.
The radar is in our like side, like plan, but it's not yet in the party.
Right.
Official.
So some paper mentioning that having radar will help the model to learn the velocity of the car, but it's really noisy, as I think most of you have already know. But so probably we cannot really use that as like a pure like sensor for like the perception model, but we can try to like have it like fused in the like whole pipeline to or like give some complementary information.
Okay, thanks.
Cool. And let's do this. Just give the last question to Ronak, and yeah, take it away, man.
Yeah, I kind of have like a two-parter. One is that you mentioned you were taking like successive frames. So I was wondering, do you use that to do velocity estimation on the cars? So once you have their pose in 2 successive frames, and you can kind of infer based on the delay between those frames, do you do velocity estimation that way or something else? The second, sorry.
Don't do that. Sorry. So for the first question, we don't do that like explicitly. I think probably the model actually learns that, but we don't have any supervision on that. Actually.
And we reached the model like not just supervised on the speed, because in that way, if the vehicle was changing speed, then the prediction was not accurate. And that's why we also do like data augmentation and flip the data, like so that the data will learn like the vehicle going forward and backward or in different speed, and so it's more generative, the model.
Right, but I think like speed is probably like a very important feature that will be actually learned by the model, even if there's no supervision. If you like I believe that if you like visualize some features from the model, there's definitely like some channel, for example, like probably corresponding to like the speed of the like different objects, I think probably. But just to clarify, we don't have that as like a supervision. So if it is learned, it's probably learned like in an implicit way. Because if you want to have the future prediction, probably it will learn the velocity at first because it helps the model to have a like rough estimate of where the car will be like in the next frame. Right?
Got it. So my second question is kind of a follow-up to that, is that do you do any kind of longer term trajectory estimation for the other vehicles?
We currently don't do that because I think our major like so I think the major reason of we have that predictive model is just like to predict, for example, like pretty near like future frames, because we just want to interpolate the LiDAR inputs like between the consecutive camera like frames. So I don't think we have actually done like pretty long like range prediction. So do you have anything to add on that?
No. I don't.
Data estimation could do that as well, right? It's not necessarily a perception problem.
Yep. So that's actually a pretty good question. I think for the future prediction or like trajectory prediction, it's kind of mostly like most paper or like most frameworks are actually done like actually like doing that in the, for example, like after the perception part, because in that case you have like the bounding boxes of all the cars, then you can basically have a more cleaner representation of the state. So the major reason that what we want to do some like future prediction in the perception like stage is because of the like discrepancy between the frequency of the LiDAR and the camera, and we want to fill in that gap.
I see. So you kind of account for the latency of the system by predicting ahead into the future.
Right. Basically, like in some frames, you probably only have the camera like inputs, but you don't have the LiDAR inputs. Then for these frames, if we can somehow like have a rough estimate of what the LiDAR could be, then we can feed them into the fusion model Matt has implemented, and we can also have a pretty estimate perception results even in these frames where the LiDAR frames are missing.
Yeah, that's great. Thanks for answering my questions. This is really nice and helpful.
Sure.
Let's go ahead and wrap up. Well, Shakar, you got a quick one? No questions are quick, but let's get this will be your last one, and then we'll let the team break, and then we could, for those at MIT, right? You can follow up with coming to join the team. That's that's the best way to get all your questions answered. But Shakar, I know you're pressed, so we'll give you the last one here.
Yeah, I'm sure you guys have thought about this, but do you guys have any plans for any pruning of the models that you have? Like last year we did YOLO pruning.
There's a lot of technique in the lab doing pruning and quantization.
Yeah, I imagine the data is very, very sparse, right? So that must, there's some optimizations that you can do to kind of deal with sparsity.
Like pruning and quantization is like a secret sauce we have, like a very mature tool. So.
Right. But actually, for although you mentioned that the data is in sparse format, actually for this type of data, it's kind of harder to have them for example prune or somehow something like that, because they're already kind of sparse and it's really irregular to process it. So there's really there are really lots of challenges of how to make the sparse convolution much faster. There's a lot of work to do.
That's really interesting, actually.
Yeah.
Yeah, maybe you can do that. You can try doing that, Ronak.
Yep.
Exactly. That's your application to the team. Just kidding. Hey, thank you all for joining our webinar, and obviously thank you for all the panelists here for doing this. You guys rock, and we're excited to hopefully continue this discussion.
Yeah, this is really awesome. Thanks, guys.
Thanks.
All right, bye.
All right, I'm gonna leave this room, and then you guys can join the other rooms if you want. They're still talking, but I figured we'll end this. Is that cool?
Okay.
Okay. Bye, everybody.
Bye.
Record.